Thank you for being here today. And as the introduction mentioned, I am a professor here at IEEE in Montreal, just up down the hill. And I lead the Multisensory Signal Analysis and Enhancement Lab. And the question that we're going to try to answer today is how can signal processing benefit AI? And I don't think I need to spend too much time. You've been here for the last 3 days. You've seen that AI is doing amazing things today. Here's an example of the latest model that came out from Google where you can give it a joke and it'll actually explain the joke to you. Other models, you give it a query and it'll write an entire book for you. So we know that AI is here to stay. It's doing excellent things. A couple of weeks ago, there was this DALL-E model that came out. You give it a text, it'll generate an image that tells you exactly what that text is doing. Here you have an example of an astronaut playing basketball with cats in space as a children's book illustration. This is what it's able to generate. We've seen self-driving cars already out in the United States and in Europe. This is all driven by artificial intelligence. So it's clear that it's here to stay. Vaccines, we're all victims, or we're all witnesses, not victims, witnesses of how AI has helped vaccines come to fruition in matters of months as opposed to years, which was the typical type of timeline for drugs and vaccines to be generated. I don't want to focus on the great things. I want to open your eyes to some of the limitations of these tools and how signal processing can potentially help with these limitations. As the old saying goes, every time you invent the ship, you're also inventing the shipwreck. So all of these excellent things, all of these tools, all of this groundbreaking work that's showing up, there are some challenges and some limitations as well. And this is what I want to kind of spend the first 15 minutes of my talk describing to you what these limitations are, what these challenges are. Some of these might be very known to you, some not as much, but hopefully you'll be able to learn what some of these challenges might be. The first that we'll tackle will be the so-called black box problem. And how do you interpret these models? Data comes in, decisions come out. What is the model doing? For some applications, such as healthcare, you need to know what the model is doing so that you can decide if the model is correct or not. Mismatch between training and testing. So suppose you train your model on a specific data set, you want to try it out in the real world, it doesn't work. It's very likely it's not going to work because of this mismatch. The model only knows what it's been given. If you now have a test scenario that's different, the model will not know what to do. So this is something that's also very critical in real world applications. As well as context. Models today are given data. This data has no context. You don't know the who, the what, the when, or the why of this data. So the model just looks for patterns in this data, and it'll make decisions based on those patterns. But as we'll see throughout the presentation, these patterns, depending on context, they actually mean very different things. So this is information that the model typically lacks. Models are very data hungry, as we'll see. We're talking about billions and billions of data points, terabytes and terabytes of data. Imagine labeling billions and billions and trillions of data points. This is not feasible. This is very expensive. So this also needs to be taken into account. Something more recent that we'll also look into, it's called an adversarial attack, where you can actually very easily fool a network to make wrong decisions while making the AI think that it's actually very confident it's making a right decision, even though it's completely wrong. So this clearly has very severe applications, especially if we're talking about healthcare. I'll also go lastly into the environmental impact of training these models. This is something that's also often overlooked. More and more it's gaining attention, but this is something I also wanted to emphasize today. And there are lots of other things, biases in data, how do you make AI ethical? I will not touch upon those today, but these are other items. If this is an area of interest to you, these are areas that might potentially be interesting to look into as well. So this black box scenario, this is a great example that showed up in the news around 2019, and it gives you a sense as to what this means. So I don't know if you followed the news in terms of AI, but around 2019, there was all over the news saying that AI is now outperforming radiologists. It's beating people at detecting pneumonia from chest X-rays, and it was all over the news. Everybody was impressed. They were saying that doctors are going to be replaced by machines, and they were reporting 93% accuracy, which was better than human-level performance at detecting pneumonia from chest X-rays. And everybody got excited. All the hospitals wanted to test this thing out. And it turned out that when they started testing them out in other hospitals, performance dropped to around 70%. Nobody knew why. Everybody started looking into it. What was it? What's the problem? And it turns out that the data they used to train this model that achieved 93% accuracy was individuals that had pneumonia. They were in bed. They couldn't get out of bed, so they had to wheel in a portable X-ray machine, and they got their chest X-ray while the person was lying down in bed. All the other control individuals that didn't have pneumonia actually went to a stand-up machine and had their X-rays taken standing up. So it turns out these X-ray machines, they generate very different images. When you're lying down versus standing up, the fluids flow around your body. They make very different images. So the machine wasn't really detecting pneumonia versus not pneumonia. It was detecting a portable X-ray machine versus a non-portable X-ray machine. And since machines are different from hospitals, they were not working. So now you have a model that you thought was detecting pneumonia, but in the end, it was detecting the type of image generated by an X-ray machine. So this black box and interpretability issue is very critical for AI research, and it's something that needs to be looked into as well. The train and testing mismatch, as I mentioned, you use some type of data to train your models, and then when you're testing your data, typically when you're in environments like this, there's going to be noise, there are going to be reflections off the wall. If you have cameras, lighting conditions will change. So these are all conditions that differ from how the data was collected when you trained the models. So here you see that when the data matches, you have very high accuracy. As soon as there's mismatch from your data, so here we're looking at different types of noise that have been added to the data. So you see that the performance starts degrading drastically. So you have a system that can correctly detect an object, it'll start making mistakes once that object no longer is a clean image, for example, but becomes distorted. So now you can imagine what type of issues this can have when you have signals collected from a wearable device, and when you start running, these signals become very, very noisy. And are you now expecting the system to perform where you're trying to monitor an individual's health, you're trying to detect things? Well, what if they're moving, if they're running, if they're exercising? If the quality of the signal goes down, is your AI always going to be making mistakes? So we need to be very careful. And when we talk about one of the things that the pandemic has also shown us is that most people bought wearable devices over the pandemic. They wanted to monitor their heart rates, they wanted to monitor their if there were oxygenation, if their oxygenation levels were okay or not. So the pandemic really boosted the sales of wearable devices. And just to give you a sense of the type of data that this can generate, within a few months from when the pandemic started, Stanford was able to run a study where they had already data from 30,000 individuals. The study has been running for the last 2 years. This has now hundreds of thousands of people submitting their data 24 hours a day, 7 days a week. So now this is the kind of big data that these AI systems need to perform. But at the end of the day, this data is what's called raw. It has no context. You feed it 24 hours of data. The model does not know. It just knows that this was your heart rate. It doesn't know if you were running, if you were sitting down, if you were playing sports. All of these things are very important for the model. So take, for example, if you have sudden changes in your heart rate, is that due to disease? Is that because you got COVID and now your heart rate is changing? Or is it just because you decided to start exercising? So context, as they say here, is the dark side of wearables, because you need to know what is happening. And this is information that should be provided to the model so that the models can make correct decisions. And then we see here the price of actually building models that outperform human-level performance. So here's a graph that tells you performance of the AI system as a function of the amount of data it was used to train. So this green line is the typical kind of machine learning algorithms from before this era of deep neural networks. So you can see that as you increase drastically the amount of labeled data, you're actually able to achieve performances that outperform human-level performance. But now, to be in this state, we're talking about big multinational corporations that have billions and billions of dollars, access to billions and billions of servers, and massive amounts of data in order to generate this thing. As it turns out, all the rest of us are down here in terms of access to amount of data and computational complexity. So now you see that it doesn't matter how complex your model is, the performance gains are not as drastic anymore, and they're not as significantly higher than what you would achieve with much simpler models. So the bulk of us actually lie here. So we need to be able to be very clever in how we process this information so that we can boost this accuracy if we want to get anywhere closer to human level performance. And as I mentioned, this adversarial attacks, this is something that has emerged in the last few years around deep neural networks. Deep neural networks are trained in a very specific way where you're trying to minimize some sort of error function, and you loop down through some error function, and you find a minimum, and that's where your model weights become optimal. It turns out that you can actually generate a very simple noise that when your model is now doing inference and it's going down this error function, you make it go in a different direction than it's supposed to go. And by going in a different direction, it'll make a decision that is very wrong, but it's very confident of this decision. And the beauty of this is that this noise is imperceptible to the human eye. So you can see that it was added to this image of a duck, where the AI system was aware that this was a duck. It was able to be very confident that this was a duck that it was classifying. By adding this noise, it is now even more confident that this is a horse. So you can see the problems that this can have in many different applications. And researchers have shown that this can be achieved with images, with speech, where you can add a specific type of noise, and you make your, for example, your Alexa system completely recognize what you're saying in a wrong manner, but being very confident. They're showing this can be true also with physiological signals, such as electrocardiograms. So now you might have doctors running remote systems monitoring individuals' heart rates. If an attacker injects some type of noise, you can now say that this person is having a cardiac arrest or an arrhythmia when in fact it isn't, or vice versa. It could be a healthy electrocardiogram, and the system is accusing that it's that the person has a certain disease. And you can see this has been shown to be, again, with many different medical images. And what's more, even more concerning, is you could, with 3 pieces of tape on a signage on the street, you could actually make an intelligent vehicle see the stop sign as a speed limit 45. So now you can drastically see the impact that these tools can have, where a vehicle, instead of stopping, it would actually speed up. So these are some of the limitations. And which leads me also to the complexity and storage. So as you mentioned in the past, I mentioned how only the big players are able to achieve those very high accuracy models because they have access to the amount of data and the complexity. So you see here where all these big players are. So this is the size of the models that they have built as a function of years. So when before the pandemic hit, this type of language model around millions of parameters was the biggest thing that was released at the time. This was in the news, this was amazing, everybody wanted to use it. Fast forward 2 years, we've gone from $340 million or 340 million parameter models to released last week from Google, 540 billion parameters. So we've gone from million to billion in a couple of years. And this is clearly not something you can store on your device, in your car. This is something that's stored in their servers. Your data needs to get sent to the cloud, processed in the cloud, and then sent back to you. So you can clearly see issues with privacy, people trying to maybe detect this data and steal this data. But more importantly, and this is something that's often overlooked, is to train these models, it actually has a significant environmental impact. In 2019, MIT did a study where, if you remember, I mentioned at the time, there was this 300 million parameter model that had come out. It was revolutionary. People started calculating the impact that training this model had in terms of CO2 emissions. So now you have to train these models on server farms with hundreds of computers running 24/7 for several months. This has an environmental impact. And what they found was, to train this model in 2019, the amount of CO2 that it emitted was the equivalent of 5 vehicles operating through their entire 10-year lifetime. So training one model was the equivalent of 5 vehicles through their 10-year lifetime. So now, fast forward to 2022, 2 weeks ago, Google came out with their 540 billion parameter model, which took 2 months to train on over 10,000 tensor processing units. So you can clearly see the impact that a model like this could have had on the environment. So this has become so critical that there are websites now that you can go to, and you can say what part of the world you're in, how many computers you use to train your models, for how long they ran for training, and it'll give you an equivalent CO2 emission equivalent, so that you have a sense of what environmental impact your model is actually having. So that was more or less the first 15 minutes kind of motivation as to why we need to do something about this. Yes, AI is great. Yes, it has great advantages and great applications, but if we're not careful, we could go into some black holes in terms of privacy, in terms of ethics, in terms of security, and also in terms of the environment. So what can we do? And what I hope to spend the next 15 minutes is convincing you that if we actually group signal processing together with AI, we might be able to solve some of these problems. We won't solve all of them, but we might be able to make a dent in some of these issues. So this slide here is to give you a motivation as to why signal processing could help. So typically when we are training these large AI systems, this is more or less the kind of scenario we're looking at. You have some noisy type of data that's being used to train your model. This data does not fully represent the signal you want to model. So if we look at this as an Alexa system, for example, where it's trying to use our voice. So your voice is the original signal that the model is trying to understand. But it's being recorded by a microphone. It's being recorded in a room that has kids screaming in the background, or it has the TV on, it has the radio on, so it has some sort of noise. So the signal that is actually used to train this model is a representation of your signal with some other artifacts thrown in. And as it turns out, these artifacts can actually be very significant. It can bury the signal of interest in a manner that it's not easy for the machine learning to actually detect and separate these signals. So that's why you need a lot and a lot of data, so that you hope that by having a very complex model with a lot of data, the model will understand what is N, what is H, and it'll be able to make this relationship with X. So that's why you need a lot of data. That's why you need very complex models. With signal processing, you could potentially process this signal. So here you see this is what that noisy signal was. The signal is buried in noise. You need a lot of data in order to for your model to understand what that signal is. Well, if you were to apply some sort of processing here, and you could boost your signal, you could make it higher compared to the noise. Now, you don't need as much data for your model to understand what that relationship is, because now the model has direct access to that signal. So you could potentially, with this, not only could you have a system that's more interpretable, you could open this black box, because now you know that your model is operating on the signal, and you know the properties of the signal that you want it to find. So if you see that it found a black spot versus a red spot, and you know that black spots are malignant cancers, it gives you some intuition as to why it was using, as opposed to just, oh, I looked at this patch here, and I don't know why I did. And again, if you're looking at less data, and you know exactly what you're looking at, you don't need very complex models anymore. You can have models that are a lot less complex, with a lot less impact on the environment, and you should be able to achieve better accuracy. So this is what we're trying to do, is we're trying to build these tools to bring signals out so that we can apply these signals to the machine learning algorithms in order to help with some of those limitations that I mentioned. And what if we could also apply signal processing here, and instead of boosting the signal from the noise, what if we could actually characterize the noise? What if we characterize what microphone was used to record this signal? What if we characterize what noise was being implemented? If we're able to then separate all of this information, you could build models that become insensitive to these environments. So it doesn't matter what noisy room you're in, it's always going to perform equally, because now you know how to characterize the noise. You can remove that information from your system. So now you have accuracies that remain consistent, whereas others will start failing after some time. And again, if you're able to detect what kind of mapping and what kind of distortions were added to your system, you could potentially detect those deep fakes or those artifacts that were added to the signal to make those erroneous decisions. So you could potentially also overcome the issue of those adversarial attacks. So this is the motivation behind some of the work and why signal processing could potentially be useful. So in the next few slides, I'll give you a very high-level overview of what signal processing is, what are some of the things that we have done in the past, and how they've helped achieve some of these things that we've promised. I won't go into too much detail here. Signal processing it's been around for many, many years. What is typical, I'm certain most of you have heard of the Fourier transform. Hopefully you've heard of the Fourier transform, is where you map a signal in time, you map it to frequency, and you can do it vice versa. The ideal is you can process signals in both domains and they will be equivalent. So what is typically done in practice is you have this time domain signal, you take a Fourier transform, so you take a little piece of the signal, you take a Fourier transform, and it tells you that for this point in time, this is what the frequency of that signal looked like. You move that window over a little bit, you take that same Fourier transform, and then you say, well, now at this second point in time, this is what the frequency of that signal looked like. And you repeat this over and over and over and over until you reach the end of your time signal, and you have what's called a frequency to time representation, which tells you any point in time, this is what the frequency of the signal looked like. This is called a spectrogram. This is widely used in many, many applications that you have in your phone, Siri, anything that uses speech relies on the spectrogram. A lot of signals that process biomedical signals take the information to the spectrogram. The reason for this is that a lot of the advances in AI, they come from image processing, they come from computer vision. So they rely on image as input. An image is a two-dimensional representation. So now, if you have a time series, such as a speech waveform or as a physiological signal, that is not an image. You need to transform that time series into an image. This is the easiest and most straightforward way to go from time series to image. So now you can take advantage of all of these models, CNNs and RNNs, and all these models that were built for computer vision, and apply them directly to speech, apply them directly to biomedical signals. But the problem is that this representation is, again, much like the one I showed before, where the signal was buried in noise. A lot of the noises we see, they overlap in time and they overlap in frequency. So this representation here is very, very noisy. And that is why today we need these very complex models with a lot of data so that we can sift this noise out from this representation. What we've proposed over the last decade is to go one step further and say, well, what if we now, this can also be seen as a time series. This is one frequency point and how it's changing over time. What if we took another transformation now across this direction and ended up with a frequency to frequency representation? This is still an image, but this is telling us how a frequency point is changing over time. And as it turns out, for speech signals, for example, I cannot change my spectrum very fast because I have limitations on my vocal cords, I have limitations on my vocal tract. So my speech is very constrained on where the frequency spectrum can change. Same thing with the heart. Your heart rate can't change as fast or it can't drop as quickly. Breathing and all of these other physiological signals for humans, they're constrained by human physiology, whereas artifacts are not. So noises, buses running by, the metro, all of these noises don't have those limitations. So by taking the second transform, we can actually separate what is signal and what is noise a lot more accurately, because now these signals, they change in very different patterns. So here's an example of an electrocardiogram. This is clean. This is with the person walking fast, and this is the person running, for example. So you can see that in time, you can get the heart rate, you can find the peaks. You can more or less do it if the person is walking. The signal has become completely useless when the person starts running. So now an AI system for sports would not work anymore because these individuals would be running, they would be in extreme scenarios. A system would not work. If you now take those two transforms and find the frequency-frequency transformation, you can now see where the signal lies. So this information in red is due to the electrocardiogram. Now you start seeing where noise and signal, how they become separable. So now you've added noise from walking. That noise starts showing up here. It wasn't there before, but you still have your cardiac information. In the extreme condition where this would have been a useless signal, this would have been a signal buried in noise. It would either made a mistake in AI, or you would need many, many, many samples to build an AI system that works. You can see that information is still here. All that noise has been there. This information is still here. So now you have a representation that has separated signal from noise, and you can make this a much better input to a model. Same for speech. You can see here a clean speech signal, increasing levels of noise to a point where the actual speech that's spoken is masked by noise. This will not be detected by any speech recognition system. If we now look at this representation, but on a three-dimensional level, where you still have frequency and frequency, but now amplitude, you can see speech information is here, and noise is showing up in this other representation here. So now again, you know where speech lies, you know where noise lies, you can separate the two. You also, if that second transformation was something that's called invertible, you can then process in this representation. So now I know this is signal, this is noise. What if I apply a filter and I keep only these components and I remove those components? So by doing this filtering, you can go from this very noisy signal where you've completely lost cardiac information into something that looks like this. This is awfully close to what the original was. It's not medical grade, but you can now recover heart rate. You can recover a lot of information from the ECG that your model before would have a hard time capturing. So this is signal processing, allowing you to boost signal information and providing a much better input to your models. Here's a quick example of how this boosts performance. You can measure the quality of the signal going in because, again, you now know where signal is, you know where noise is. You can measure a signal-to-noise ratio. Signal-to-noise ratio gives you an indication of the quality of the signal. So if you now have a sense of the quality of the signal, you can have that information into your model, and your model now can be aware, oh, this is a very noisy signal, I need to do something else. Oh, this is a clean signal, I can make my decision straightforward. And that gives you much better performance in practice. Context, again, we're able to, you can see when the person is walking or when the person is sitting. I showed you in the previous slide, the signals change drastically. What one would typically do is, well, let's filter this signal, let's remove the noise, let's throw the noise away. What we are showing is that don't throw the noise away. The noise is actually a very useful tool to measure context. So here you can see by processing the noise, we've been able to characterize when the person was sitting, when the person was walking, and when the person was running. Because those different activities generate different patterns in the noise signals. So now if you mine that noise, you'll be able to infer context. Same was true with the speech signals. We can infer, we can separate what is noise, and instead of throwing this noise away, we can actually characterize it, understand it, and we've shown that you can actually detect where a person is in any particular point in time, from size of the room to how many people are around them, if you're indoors to outdoors, or if you're actually inside a car or a bus. So why is this important? It turns out that context is crucial to make systems operable in real time. And not only is it important to make systems operable, but if you recall that slide that I had in the beginning where amount of data and where the regime where we are, there's not a lot of change between traditional machine learning versus deep learning. We're showing that, indeed, when you have limited data and you don't have context, it doesn't really matter. Your machine learning, it doesn't matter if it's shallow or very deep, it's not going to change the accuracy, it's going to be almost the same. But if you provided some cleverness, if you provided some context, if you provide information about the quality, you're able to boost this performance in such a way that even with traditional machine learning algorithms that operate at a fraction of the computational power, you can actually outperform these models. So if you are in a regime where data is limited, use signal processing, use some of this intelligence so that you can boost performance and not fall into the pit of the deep learning limitations that we saw. Again, adversarial attacks. Here's an example of, it wasn't supposed to be sideways, but this is supposed to be a chest x-ray for a patient with COVID. This has been tampered. To the naked eye is not very clear, but there are tools that have been around for many, many years that try to characterize information in an image. It tries to characterize the naturalness of an image, the amount of distortions, the amount of blurriness. This has been around for years because this is needed to characterize compression algorithms that we use in our cell phones, JPEG and so on. It generates distortions that need to be quantified. And we show that by detecting these distortions and quantifying them, we can very accurately detect these adversarial attacks to images. And same is true for speech. In terms of interpretability, as I mentioned before, here's an example of a study where we ran using brainwaves trying to detect Alzheimer's disease. And a lot of the systems rely again on the spectrogram. Spectrogram is noisy, especially with EEG where any head movement generates noise. So by doing this frequency transformation, you can clearly see here already some of the changes that it generates. So by applying this as an input to a neural network and looking at the activations of the neural network, we're able to see where from the image the neural network is focusing their decisions on. And now, since we have a representation that's a lot more natural and a lot more interpretable because we now focused on only the regime that we know is affected by Alzheimer's, we can actually not only boost performance, But when we correlate those regions with fMRIs, we see that they're the only ones that actually show some relationship with structural changes with MRI. So now you can measure relationships between these features that you have found and actual neuroanatomical measures. These correlations were also shown, for example, in hemodynamics. We know that the brain has plaques when you have Alzheimer's and blood flow becomes impaired. So now you can interpret why that model chose these specific regions, because these regions correlate with some of the damage that's done in the MRI and some of the damage that's done from blood flow. So you're able to now also boost that interpretability that we saw was important for machine learning. So in conclusion, we started out today with the question, can signal processing help AI? And I hope I've convinced you that the answer is yes. Again, as I said, we are only here in this presentation touching the tip of the iceberg. When it comes to AI, there's a lot of other things and issues and challenges and limitations that need to be addressed. I leave this here for you. If this is an area of interest, these are all things that will need to potentially be looked into and explored. None of this would have been possible without the students in the lab and the funding. I leave here lab's website and some of our social media where we post a lot of our work and publications and so on.